Hello everyone, this is Alice in Beijing. I'm so glad to meet you again on this I Can X Talks. Actually, after a long holiday, I mean in mainland China this week, a long holiday for everyone to celebrate for the National Day. So many people so hopefully already enjoy to travel somewhere. Maybe not that far away as Europe, but you already see that COVID-19 is almost in control in mainland China. But I hope, yeah, we got good news from everywhere as COVID-19 will be in control in the near future, like in China. So yeah, we will come back to ICANX talks. Everyone knows that. Yeah, we ICANX talks never stopped. Last week we have two super speakers, Julia and Carl, from US and from Canada. And this week we're going to have, three young generations, young scientists, young superstars. Yeah, why say that? Because I already met them. One is Junsuk Rho from Korea. And another one was Huilin Shao. Another one was Xianting Ding from China. Huilin was from Singapore. So I met them a few months ago on Mine 2020. This was a Young Scientist Award selection. So we have 60, young scientists join the competition. So three of them win the title. So they are superstars. They already done a lot of nice work. Though they are pretty young, but they are being the stars in the field. And today they're going to, distribute a very nice talk. So first we welcome Professor Dr. Miso Kim from Korea to introduce her classmates, right? Her mentor, yeah, Junsuk Rho. So please, Miso, it's your turn. Hi, I'm Mitra Kim again. Today I'm serving as a chair to introduce participants of growth, and I'm very happy to have a chance to introduce one of the most productive and innovative scholars of persons of growth, whom I have known for about.
And also the Department of Chemical Engineering at Pohang University of Science and Technology, aka POSTECH, Korea. And he received his BS at Seoul National University in the Department of Mechanical Engineering, and he got his MS at the University of Illinois Urbana-Champaign, and he did his PhD at Berkeley, again in the mechanical engineering department. After that, he worked as a postdoctoral fellow at Lawrence Berkeley National Laboratory and also at Argonne National Laboratory. Professor Rowe has published approximately, I guess, more than 100 high-impact peer-reviewed journal papers, including Nature, Science, Nature Materials, and Nature Photonics, and Nature Communications. I envy him. And he has received numerous honorable awards. He has quite a list here, so I'm not going to list all of them. And he's going to add one more today, the Spring Nature Mind Young Scientist Award. And big congratulations. And he's gonna share the seminar. It's his great seminar with the title of Hyperbolic Metamaterials and Super Resolution Imaging. Big congratulations, and the award is yours.
Okay, so um, okay, can I now I can share the slide, right? So thank you very much, Professor Zhang and Dr. Kim for introduction, and I'm very honored to present this work in this ICANX symposium. So yeah, actually the today's main topic is about biomedical engineering. So I'm doing a little bit of this biophysics and like doing microscopy, but most of the approach is from optics and material science. So today my main objective is it showed, called about the metamaterials, a new emerging material science, and how it can be applied to the super resolution imaging. So it's about, microscopy. So we can use this one for, I aim to do for like a biological imaging with the super resolution, like I cannot say competing, but we have a lot of good super resolution technique like STED and STORM, TEM, and so on. But it has some own benefits. So you may see what's going on in this field. So main idea is hyperbolic metamaterial and super resolution imaging like lens, super lens, hyperlens, and so on. Okay, so I'm in Pohang. POSTECH, I share 2 minutes for where is it POSTECH. Pohang Seoul is here in Chun here, so quite far from East Coast. We're located in nearby Busan, Ulsan. It's an industrial city made by our mother company POSCO, actually doing steel industry, making iron. So they made this company for like 30 years ago. So some very small campus. We have only 400 faculty, but student, you can see we only admit 300 every year. So very small. Our actual like a role model was like Caltech. So very small, but we all fund the students. So that's still we are doing so small university. One famous stuff is in we have only this accelerator in Korea, so third generation, this synchrotron and this fourth generation free electron laser, so XFEL. So this try to attract more scientists in Asia and even in Korea. So this is our some famous stuff in university. And maybe sorry for the long, the old ranking about like under 50 minutes, 50 years old under. So we were number one in 2012, 13, 14. Now I believe it like HKUST and Nanyang Technology University was number one this year. So it's, anyway, we're competing with the KAIST and EPFL and so on. So, different ranking this is from QS ranking. So you see NTU, overall the trend is similar, NTU, HKUST, and City University Hong Kong. And this is maybe more compatible, like a small university, like NTU, HKUST is bigger than us. KAIST is also. So Caltech and Ecole Polytechnique and then POSTECH. So anyway, we are trying to strive to do best science in the world. So please see what we are doing. Okay, so let me start now the scientific theme. So this is the overall, general technology development curve. So you can see here the building basis mean like a science, and this mature stage is called like a technology or engineering. So today I'm gonna compare like a micro and nano or electronics and photonics. So usually, from starting from science, some breakthrough happen. Until before that, many of the science is just stay in science. But you can see current pandemic and few years ago, artificial intelligence boom, like the Weiqi in AlphaGo and Korean this master Lee. After that, many people, industry, even normal people interested in this artificial intelligence and corona and all the virus stuff. And then after that, like immediate, a lot of money and time. So some of this science go to technology, but not all, like less than 5%. But you can see like a micro technology or electronics is already mature level. So we have a daily life benefit from this technology. But you can see the nano or some like let's say comparing electronics photonics still in many this level. So I'm gonna show today the result is also how we can make a demonstration breakthrough starting from scientific fundamental. So I share the how we can realize the super resolution microscopy by metamaterial, but still in the proof of concept stage right now. But I'm having engineering background, so I'm trying to show what I am, making effort to making this science, making this technology. So hope this, this super resolution imaging device, everybody can use using your cell phone and so like a small camera, LiDAR, and so on. So hopefully you can see, make sure this nano, whatever, nano optics, quantum nanobio is still a lot of way to go. So we have to do work very hard. So then what is metamaterial? So this is where familiar, materials definition. Like we are familiar with this, like a gold and quartz is different material because their chemical component is different. Gold is, the minimum, smallest dimension, consists of gold is like gold atom, right? It's the smallest, component, and quartz is made by different atom. So atom is different, so materials, different. This is quite obvious. And although same carbon, we know the graphite, the diamond, graphene, nanotube, all have different property, mechanical, optical, thermal, and property. And based on this bonding, chemically, how they are bonded each other, the material property are different. But this is all chemistry-based, material science. But the metamaterial is, simple definition is like here. Structured material, artificially made. So artificially made material is like candidate for metamaterial. But based on this, we have to make this atom artificially. So you can see this is all this made by like nanofabrication, microfabrication. So this is one atom. So you can imagine like a Lego block. So you have like a 1x1, 2x2 square the Lego block, and you can make everything, right? But still there is a limitation. You can only stack, not full 3D, 2.5D. But anyway, you can compare this Lego block as this meta atom. So we make atom and like a molecule, and we can put each other and making cluster, and then make a 2D surface, and then eventually 3D material. So how we can position, how we can place this atom, so physically, so rather than chemically, so that determines the material property. And those material properties should be very extraordinary, unprecedented. It's like cloaking, invisibility cloaking, negative refraction, and so on. But only the important thing is here, the atom size should be very smaller than given wavelength, the interacting wavelength, like a visible light, like a 400 nanometer, and then this dimension of A should be not exact definition, but maybe smaller than 100 nanometer, maybe. But smaller is better because we don't create a new atom. So this atom is made by existing material, existing fabrication. Let's say I made this one with gold, some structure, nanorod. So, but if that is too big, that nanorod is like a 400 nanometer size and pitch, and then this light comes in, interact with this material, and just consider this. Oh, this is gold. Okay, I'm gonna show the optical property, with regard to gold. But if this go to very small, and light is like confused. What is this? So now the light see what is the structure, what happened here. So that is subdiffraction scale. So I'm gonna explain again one more time this one. So anyway, this is the scientific definition of a metamaterial. And then now metamaterial is expanded to all broad of wave. So acoustic, elastic, and earthquake wave, and so on. But mainly, I'm gonna consider today optical metamaterial is in electromagnetic wave domain. So important stuff is epsilon, electrical property, and this mu, magnetic permeability. So the first phase here is like a positive index, like dielectric. So dielectric has a fixed refractive index like water 1.3 and silicon 3.5. But people demonstrate using this metamaterial concept like an index of 50, larger than 50 times larger than index of air. So they can make a light become slower, and also they can make zero index, and then like go very faster there. And then this is here is like a metal area. Here is a magnetic material. But here, third plane used to be known no existence of such material. Epsilon, mu, both negative number, it doesn't exist in nature. So people didn't ignore, people ignore here, but people found this exists. So epsilon mu, both negative number, and we can achieve like a negative index material. So Snell's law become reverse. So using this concept, in the first proof of concept is that we can achieve like a perfect lens, uh, highest resolution without any loss, making a perfect lens. And then people use this concept for invisibility cloaking and super resolution microscopy, what I'm doing, and chiral sensor and so on. So a lot of application is ongoing. So, and today main idea I'm gonna share is like another uh, field of a metamaterial called hyperbolic. Hyperbolic is like, dispersion of epsilon is, shape is a hyperbolic. And we can control this epsilon, either plus, minus, smaller, larger. We can engineer depending on what we want. Usually epsilon is a fixed number and given wavelength. So property epsilon of a certain material is given, but we can engineer by this, like using the metamaterial, meta atom placement and so on. So I'll show the detail a little more later. And then many of application trying to do, because already this metamaterial is more than 20 years. Uh, but people is waiting, not right now it's a science level, but people waiting. So metamaterial may change the world, but so hope usually become hype. So they didn't didn't change the world. So we don't want that. So we strive to making striking advancing, like using this metamaterial lens, integrating with the cell phone and camera and optical device, and this is like an arbitrary skin cloaking device. It's like a clothes. Real, we can wear this cloaking device, but still the scale is very small. So we have a lot of to go to in terms of manufacturing. So this is another thing I'm gonna share today. So continuing such a beautiful science, our group is also working on many different fields like metasurface hologram and thin lens and cavity laser, chiral metamaterial, and also artificial intelligence and so on. But today, only have 30 minutes, so I'm gonna share this. What is the hyperbolic metamaterial and how it can be used for good microscopy. And then, why do we need, good microscopy? Have you ever thought about, do you want to, if you have a telescope and your camera is a resolution is not good enough, so you may, complain, right? So here is one picture I took, anybody can tell this is a car or motorcycle. Car is like having two headlight, and motorcycle has a one headlight, assuming. Not sure, it looks like one, right? But it can come closer to me. I took another picture, so you can see this circular pattern become little like an elliptical shape in x-directional elongation, right? So I have some suspect, like, oh, maybe this is two headlights. It looks like car, but not 100% sure, right? And come little more, now I can clearly see, okay, this is two headlight, so it's a car, but if far from too far, I cannot distinguish these two light source. That's the problem. We meet the resolution issue in our daily life. And same thing happen in the micro nano scale. Let's say you have two laser pointer or two quantum dot. You want to make a quantum dot blinking to making some color and light source, but if they are too close and you don't see they are two or one, just we see one big airy pattern is propagating. So, oh, I'm not sure this is one quantum dot or two. So, and we make a little further. Okay, this airy pattern is looks like a two. So it is two, make sure. But where is the center point? It's very strange, hard to tell 100% sure. But I can tell this is two. And further enough, now I can tell here is a center point, center to center distance is, blah, blah, and, two airy pattern, two light source. And then this is, is comparable to this picture here. And the second picture, so this is called like a diffraction limit. fundamental, long, or historical problem in optics. So making harder good microscopy. Due to this diffraction limit, microscopy is always struggling to make a better one. So diffraction limit is a two light source, we can distinguish or not. So critical point. And why it happens. So here is my interpretation. So object is here, and this is like optics, lens and or whatever, camera and so on. So this is image plane. So light comes in here, and light hit this object, and then deliver the image passing through this lens and image plane. So the propagating wave called, and this is like a moving stuff, and they deliver this big size information, like an outline of the some object and some big size information. And this is correspond to the small wave vector k. If you write down the equation of a wave equation, so k is small. So this is, this guy is doing work very well. So deliver the information with the sinusoidal wave. So deliver information from A to here, object to image plane. But the problem is this guy's evanescent wave. So this guy is carrying the small size information. It's very detailed, like a small list, some small information. But evanescent means it's vanishing, decaying. So you can see this is a heat. Evanescent wave is generated and doesn't, they don't go here. Just exponentially decay. Travel a little bit in up to near field limit, few hundred nanometer invisible, and then just gone. So loss of information in evanescent wave make a worse resolution here. And then people, people are smart, so many scientists try to catch this evanescent wave directly using like near field microscopy, AFM, and so on. But AFM and some is a very good technique. Resolution is 50 nanometer less than, but this is scanning time. The take a very long time, and it's like not like a direct imaging. So we take a time and some image happen, but we have to wait a long time. So not it's like a far field imaging device, like a light microscopy. So like 10 years ago, we thought about what we can do to solve this problem. So this is a very small object, subdiffraction scale, optics, image plane, and light comes in from here to here. So this happened. So image is distorted due to information is not delivered from here to here, due to evanescent wave is lost around here. So what we need is we need a certain device. This device is like a projector. So what this device is doing, capture the evanescent wave before they are just decaying, and then converts it to propagating wave, like a projector. So let them go to the far field. So we need such a device. That is our objective. And function this guy is doing is converting evanescent wave to propagating wave. This is a function. And what we need, this material or this device has to have this high K vector access. High K means like a higher resolution and evanescent wave. And then more simply speaking, high K vector access, we need a high refractive index. So that's our simple goal. Okay, so here is just one simple mathematics, high school mathematics. The dispersion relation is talking about K wave vector is a resolution, high K is a good resolution, epsilon permittivity given property of the material. Like if you use a glass lens, it's epsilon is given for glass corresponding to your wavelength, and omega is our given wavelength. But the problem is here, okay? Epsilon XYZ. Let's say we have like here air and quartz. It is a naturally available material, and they have isotropic. We call they are isotropic, which means epsilon XYZ are same. So air, water, glass, they act samely in regardless of their direction XYZ, right? And epsilon XYZ has the same number and same sign. So if you put this epsilon X and Z into this equation, what you get? Like a circle, right? In 3D, it's a sphere, and circle is comes out. And this is like the radius of this circle is a refractive index. Air is 1, quartz is 1.45, right? But the problem is here. So this is the object we have to see. If you do Fourier transform of this small object, it's located here, let's say. And then what happened here, let's say object size is very small, but our glass material is like a fixed refractive index, so this arrow cannot go outside, which means evanescent wave is naturally happen. You know, this go here, and perpendicular direction is pointing back the direction, propagation direction of the wave. So this is a normal case of refractive index is lower, so evanescent wave happen, so low resolution. So ideal solution is here. Very high refractive index like a 15, 20, and then very simple. Index is large enough, and this is very easy to making propagating this direction. And so no resolution issue. But the problem is in nature, such a material don't exist. That's the problem. So people also, smart, clever, so that people try to understand what physicists can do. We know only 3 equations: circle, elliptical, and hyperbolic, right? So first the trial was making elliptically anisotropic medium. So actually naturally exists such material recently discovered, like hexagonal boron nitride, or some of some 2D material have some anisotropic property. So but not very few, very not easy. So this is one case we can make elliptical material by nanostructuring or microstructuring. Sacrificing the refractive index in Z direction, we make X direction resolution refractive index higher. So in certain case, we have a large this arrow, large refractive index, and we can make this touch this arrow here. So sometimes work, but this ellipse or intrinsically they have the boundary, so not like ideal, very good solution, although they can solve the problem. So final case, like remaining one is a hyperbolic case, like epsilon, if we have epsilon plus plus minus sign. And then from this equation, you have like a hyperbolic dispersion. And hyperbolic doesn't have, like they have asymptotic line here. So, refractive index theoretically, in principle, can be infinite, right? So, but not in reality, actually. But anyway, so this arrow refractive index is large enough touch here, and now this is a actual propagating wave direction of the this given this system. So evanescent wave is already converted to propagating wave, so they can have a physical moving. So this is what we need in mathematically, physically, plus plus minus epsilon material in different X, Y, Z direction. So far, so many of the ways found, how to achieve such hyperbolic dispersion. So here is a simple case is making, it's like optical alloy. So metal dielectric, we can, it's like sandwich layer. This is, thickness is too large, like 400 nanometer each, like comes in, and they distinguish, okay, this is silver, this is titanium oxide. So they do interact with regard to the property of silver and titanium oxide. But the thickness is too thin, like 20 nanometer, and then like comes in and they don't know what it is. So, okay, this is new material. Let me interact with this guy, with this guy's property. And the new property is given like here. New epsilon XYZ is come from original epsilon M, epsilon D, and P is like a ratio, filling ratio, thickness ratio. So we can control somehow depending on material and their physical, this configuration. So this is average value. So if we got some certain number plus plus minus, so that's it. That's our goal is done. And then what happened to such a material? So this is air, this simulation result, 50 nanometer distance, and this is a light comes in, and light travel a little bit. So this is a near field limit. So no far field here. But such a material, hyperbolic, they can making the light travel to long distance inside of this material due to the certain this dispersion relation supported by this hyperbolic. But the problem is this we don't see the cross section of this material. Anyway, it has to come out to see seen by us. So this is again air. So again, you can see near field gone, evanescent wave. So this is not again not the best solution. Although we could control the light in the subdiffraction regime. So what we applied here, so made a simple geometrical effect of a sphere or cylinder. What happened here? Initially 50 nanometer distance, but they can go to perpendicular, and then their separation happen. So 50 nanometer, 400 nanometer. So and if that 400 nanometer is very easily easily resolved by simple microscopy like objective lens. So this is our concept. So 2D super resolution, maybe subdiffraction resolution with the spherical geometry, and hyperbolic dispersion supported by this metal dielectric multi-layer. So silver, titanium oxide, and this work for in this visible wavelength. So not unique solution. They have many of possibility. And then one more some detailed explanation here. Like comes in, this is very small object. So start of propagating. So that is the location is here in this dispersion relation. And they traveling here, what happened? Momentum of this light is Rk is conserved, the same value. But R become larger, so K becomes smaller. So K is following this hyperbolic line, go here. And then this point here is like this intersection of this hyperbolic material and glass. And now what happened? This glass is have enough refractive index here because it's already become very smaller comparing point A. So now glass can let propagate this light, so they can travel to far field. So we compress the K, which means magnifying. So originally 500 nanometer is magnified to 400 nanometer, which means K, large K become small K. So they can go far field. So that is a converting mechanism, simply. So, okay, time is pretty closing to end. So I'm gonna skip this slide. So fabrication side, I'm gonna only make a drill hole by FIB. So this is a bottleneck process when we do manufacturing. So I'm gonna compare in the few slides later and make this spherical geometry by HF and the evaporation of a metal dielectric multi-layer, and we put the object here. So we put object here, we see. And what happened here, we experiment is very simple. We integrated with the objective, very simple light microscopy, and the CCD camera is a real-time recording. So we don't do any vacuum, no electron, and real-time imaging. So not like a storm and instead a localization microscopy. So this is our object, 160 nanometer. So if you do shine the light in normal lens, normal material, you don't see anything. This is like a 3-hole was not resolved. So this is obvious, right? But if the case of hyperbolic metamaterial lens, you can see the image of this smiling face. And region 160 nanometer is magnified to 480, 3 times larger. And this number is very easily captured by this oil immersion lens and real-time recording. So this is very good strength of our technique. So we demonstrate a lot of stuff, but the problem happened here. So okay, after the demonstration here, I thought like this is not practically useful. This is a good demonstration, breakthrough. So I thought about if it can, solve the problem in the medical science, biological imaging, it make a breakthrough, like imaging of a virus, like 100 nanometer resolution. Now we are using cryo-EM or storm instead, very expensive technique. But if you do using this very simple microscopy, it's game changer. So I tried to this neuron imaging with this hyperlens, but in the beginning was very difficult. Try to put this neuron or cell in the groove of this hyperlens, but they are moving, and also this capillary force make these guys go here, and very hard to position here. So I tried to using this optical tweezer, combine this neuron into this dielectric bead, but this also this optical tweezer is a very low throughput technique, so very hard to do. So not practically useful, I realized. And then challenge was how to make this one happen. So what at the time what I realized in here, all the hyperlens, not just by me, many different guys do hyperlens, but all hyperlens is hard to make. That's the problem, very expensive. To making this hyperlens, few $1,000 and even few tens of $1,000, and trying to put the neuron here is extremely difficult. So that was a problem. So I thought about what's the problem of this nanofabrication. So nanofabrication is slow, expensive. So we needed some new manufacturing technique like a microfabrication, semiconductor technology. So simply we applied the nano imprinting to making a lot of lens in the single device, previously like a one or two device. But now in one wafer, we have like millions of these hyperlens and put the biological stuff here and trying to see, that's much, much easier. So we replace of this FIB focused ion milling process with the nano imprinting. So one printing or place as a whole, and then we can define this sphere, and then everything the remaining stuff is same. So, and then also some good point is we can make easily replica by this, solidification of a glass and like a polymer. So now we can make this hyperlens like less than $10. So previously like $10,000. So this is a wafer. So now we can cut very small size and make some like a optical filter. So we do packaging and then put the microscopy. So you pay $10 and then you have a resolution of 2 times, 3 times higher. So you can see 100 nanometer with your microscopy without any like technique. So that's our concept. So as a proof of concept, we images a live neuron into this hyperlens array. So resolution was about 120 nanometer, and we could see they are moving, but still the highest resolution here should be smaller than like 50 nanometer to see the actual like a synapse and so on. But anyway, so this is first time demonstration of real time biological imaging. So that was the good thing, I think. And then now we are doing, last few minutes, we are trying to making this one to technology. So microscopy, every lab has this one, like more than one. And then $10 this optical device and like 80 nanometer resolution, you see something important in like a virus and cell, and then you do cryo-EM, storm. And then you can save a lot of time and money. So that's our some target using this metamaterial lens, covering 50 nanometer, between 50 nanometer and 150 nanometer. So $10. So that's our concept. So we're trying to making this technology using engineering, like a thin film quality, less than 10 nanometer, and waterproof and packaging, and making some prototype of a model to integrate with the microscopy. So if it happened, so I cannot show the prototype due to some IP issue right now. So maybe we can do like how this virus bacteriophagy landing pinning injection is a cryo-EM image. So maybe you can see the dynamic image of what this guy is doing. So maybe 5 years later, I can show the final result, like ion transporting is taken by cryo-EM also. So what I show, two-dimensional metamaterial-based hyperlens doing real-time super resolution, but they don't need no electron. They don't need electron vacuum. So maybe good for biological imaging. So what we are doing right now, making this a bio nanoscopic component, maybe module. So we are doing. So this is the, you can remind the first slide. This is a science like 12 years ago. Now we are going to technology. So maybe middle of some place. So trying to support it by manufacturing support and like packaging and some engineering stuff. So maybe 5 years later we can go to technology. So but I can tell you the hyperbolic metamaterial has a very diverse application you can do. Right? Just to tell today, imaging, but they can do this making small little laser, making nano cavity to capture the light and make a laser. And reverse of this hyperlens can make this nano focusing lithography. And also they can use for observe the extraordinary optical phenomena like a negative refraction, optical spinel effect, and so on. So if you so this hyperbolic metametry is not just doing microscopy, but also they can do many different things. So this should be my last slide. So last year, the World Economic Forum announced like 10 emerging technology last year. So number 3 was a metamaterial based lens. So the comment was a metamaterial lens is very good and blah blah, but the problem is manufacturing cost is too high at this moment. So manufacturing revolution should be accompanied to achieve this metamaterial based lens become reality. So that was a last comment. So I'm gonna skip the another meta lens. So okay, sorry for this. Actually, so this is applied to real this biological cell imaging, so they can increase the resolution comparing the normal confocal microscopy. So metamaterial is very good. I hope so, but still, so far good demonstration. But what we need, manufacturing revolution to making large scale. But this is not only problem. There are another many problem. So how we can achieve 3D structure, how we can make an active function. So right now it's a passive device. So then and so on. So and then we can get real application for useful for daily life. So nano is still a long way to go. So sorry for this, but that means we have something to do. So I focus on few reference here, but all the work is it is compressed in our today's talk. So thank you for my student in our lab. So I'm gonna maybe the right time, cause thank you very much. So if you have any questions, I try to answer. If you cannot ask, you can send the email later. So thank you very much.
Thank you very much for your great talk. So we already have a number of questions for you. So the number one is Professor Rho, very interesting talk about metamaterial. The precision control of each layer's thickness in large area is very hard. Do you have any comments on this?
Yeah, indeed, so far, so the fabrication effort is like a real, we need like a real fabrication master. So all the each process, you need a very precise control of the thickness, roughness, and everything. So you can imagine like a 10 nanometer, for example, so far we use like a 20 nanometer thickness of silver. But to make this lens efficiency higher, we need like a thinner layer, like 10 nanometer. But the 10 nanometer silver is usually very hard to achieve, like an island stub of silver. So we need a very precise control supported by some surface chemistry and so on. So this is very hard. So maybe we myself cannot solve everything. So but if my humble opinion is like if industry are interested in this, like Samsung, Intel, Applied Material, they have this very high vacuum spotter and ALD technique. So for sure they can solve this problem. But in the lab level, demonstration level, I have to admit this is very difficult. So very good point. Thank you very much.
Okay, great. So the next one is metamaterials is very hot topic, but not coming to market yet. In your view, what will be metamaterials killer applications?
Yeah,
Yeah,
so
I'm
if
curious also.
yeah, if I knew this, I should have done this one before. But everybody waiting. Yeah, many people, all the government and all funded agency, waiting the real metamaterial, product. So myself believe, I'm doing this microscopy. So I hope my this microscopy can be used for all this optics industry, but not yet. And but people trying to do launch the antenna. Antenna is like a microwave RF, or using for like the replacing stealth, all the type of stealth technique. So indeed, a few company in US and Europe and even China, China, the institute named Huangqi in Shenzhen, so they based antenna making high resolution radar and like a perfect absorber, perfect reflector for military application. So that would be one thing. And recently, more serious application people are interested in is like a, hologram or some new display, AR device, VR, or very thin lens. Actually, Samsung is making this metamaterial based lens to making IR image sensor. So I believe, at most within 10 years, you will see something. You have the name of a Meta in product. So, but it's a very difficult question.
I'm looking forward to it too. And I guess we have one more question, but it's not on. Yeah. For Hyperlens research, what kind of microscopy is used? Okay. Does it need any software to match?
Yeah, this is the strong point of this Hyperlens. You don't need any fancy microscope. So just a simple wide field light microscopy. Maybe how much is $10,000. So most of the lab have this one. So you just put this Hyperlens device, and you should have objective and just engage it with the oil and air, and then that's it. So light source is a simple, no, no, just a simple illumination of white light. So you don't need any filter and no this any other component. Then software wise, you just use your own stuff. So no special program. But you may need some good CCD camera because the currently Hyperlens transmission efficiency is not very high. So about 40-50%. So you need some relatively good CCD, but that's it. Yeah. So, okay.
Okay, sounds great. So I guess now it's time for me to deliver honorably to deliver the certificate for you. So big congratulations again for your great award, and you deserve it. And we are very, very proud of you. So here is your virtual certificate, and you'll get the electronic file later. And
Thank you.
congratulations again.
Thank you
I'm
very
so
much
proud of
all.
you.
Okay. Thank
Okay,
you.
thank you very much. Thank you very